All right, so now it's time. So shall we get started?
Sure.
All right, so welcome everyone. This is very early in the morning in Korea, but and still many of us are here. And thank you all for coming. And it's my great pleasure to have Hiroshi Oguri as our first plenary speaker of the morning session. And he's going to tell us about stringy resolutions of null singularities.
Hi, thank you. So good morning, good afternoon, good evening, good night, whatever time zone you are. Thank you for the kind invitation. So I'd like to talk about stringy resolution to a couple of null singularities that appear in the context of AGS GFT correspondence. And both are in collaboration with Matthew Dodelson. Matthew has been the postdoc at the Calgary IPMU for the last 3 years, and he's moving on to CERN this fall. And so we have been interested in the kind of singularities that come from the existence of null geodesics. And singularity in Green's function due to null geodesic have been known since the time of Jack Adler in 19th century. So for example, if you solve Klein-Gordon equation, even when you have a mass to the Klein-Gordon equation, the Green's function generically have singularity along right cone. And so that immediately gives rise also to singularity in various physical quantity you can calculate in perturbative method, perturbative in quantum field theory. But then that raised some puzzle about the kind of singularity and that existence of singularity expected from this kind of Adler singularity sometimes get in contradiction with our physics expectations. And interestingly, so I will talk about the two of such kind of null singularities. And interestingly, in both cases, singularities are resolved by stringy properties. So it's kind of an interesting situation where consistency, in particular with ADS-CFT correspondence, requires extended object in description of gravitational theory. So the first kind of singularity I would like to talk about is bulk point singularity. And this comes from what's called Landau singularity in conformal field theory and ADS dual. So it has been known since the time of Landau that if you have some interaction point which can be connected to external point by null geodesics, then that can give rise to singularities. But if you have ADS-CFT correspondence, such singularity can exist when light-like geodesic stays only on the boundary, in which case you would expect the CFT correlation function to have singularities. But there can be a situation where there are bulk points which can potentially give rise to Landau singularity, but there are no corresponding boundary Landau singularity. So you would not expect in such a case singularity to arise in CFT correlation function. And in fact, one can show that one can easily calculate that, oh yeah, so maybe I should go back and say that it was pointed out by from Aldacena, David Simon-Zaffin, and Sasha Ziboedov, that there are such cases where you can have a bulk point in ADS where you have potential Landau singularities, but there are no, you do not expect Landau singularity from the point of view of boundary CFT. So Matthew and I are interested in, so they suggested a way that this can be resolved, but Matthew and I were interested in quantifying how this can be resolved. And so we did it as a kind of exercise for more interesting case that in the cases that we are more interested in involving a black hole. But let me discuss this case first. So we formulated a criteria for absence of such unphysical singularities. And the criteria is the following. So it has been known that if you have CFT correlation function on sphere, and then you can actually perform Mellin transform to write correlation function in terms of Mellin amplitude that is consistent with conformal symmetries. So Matthew and I pointed out that such correlation function, in order for such correlation function not to have unphysical Landau singularity, but only Landau singularity expected from the boundary CFT point of view, then this Mellin amplitude should be bounded in high energy like this. So what are the conditions for this to be satisfied? So to see that, we use this formula proposed by Penedones, relating this Mery amplitude to flat space amplitude. So when you consider the situation where the bulk point is connected to a boundary point by null geodesics, that you expect that the interactions are very focused at the local point, where flat space scattering amplitude can be utilized to estimate this effect. So Penedones actually proposed the explicit formula for this. And so we're going to utilize this. And so this is actually flat space amplitude. And so then we can see that, in fact, if you utilize flat point scattering amplitude, typically it scales like some power of energy for high energy, in which case the Mery amplitude also scale like same power. So that means that if, for example, the boundary conformal dimension is sufficiently large, this would contradict with this bound that we require. But we found that if you have stringy behavior, then it's different, because in that case, high energy behavior of scattering amplitude is softer. And so then the Mery amplitude decays like that. And in fact, it decays faster than required by this bound with some margin. So this is sort of the way that the bulk singularity is resolved. Okay, so this is the first story that I wanted to tell you. So by the way, so I'd be happy to take questions during my talk, but it's hard for me to pay attention to chat box during the talk. So probably Jaewon can alert me if there are some questions. And if this is going to be a long conversation, I would like to leave it to Q&A. Okay, so that was a short story, and I would like to tell you a little bit longer story, which has to do with the resolution of singularity that you can expect, but are unphysical, that can happen from due to light-like geodesic going around the photon sphere of black hole. Okay, so here in this case, we consider, again, in the context of ADS CFD correspondence, ADS Schwarzschild geometry, and this is a cartoon of ADS Schwarzschild geometry, and that describes the finite temperature correlation function in conformal field theory, finite temperature conformal field theory, excuse me. And suppose you calculate 2-point function. So then again, you'd expect that where 2-point function can be calculated just in the point particle limit, just calculating the Green's function in the bulk. So then using the insight from the days of Adamar, that you'd expect that if these 2 points are connected by null geodesics, then you would have a singularity for this 2-point function. But it turns out that some of these singularities are unphysical from the point of view of CFT, so should not be there. And so we'd like to discuss how this can be resolved. So what kind of mechanism would make this consistent with physics expectation? So first of all, so there is a time direction going this way, and there is a spatial direction. I assume spatial direction on the boundary is a sphere. So if you have 2 points on the sphere, so suppose you project down to the same time, then you have 2 points on the sphere, and you can always put them on large circle. And if you do that, then without loss of generality, you can assume that there is an angle between these 2 points. And if you want to connect these 2 points by light-like geodesic, then what you'd expect, you'd find it that there are light-like geodesic when the time separation is equal to plus or minus of angle separation mod 2 pi. So if you approach to this point, then you'd expect this type of singularity. So these are kind of singularities that you expect for the boundary CFT. But from bulk perspective, there are more singularities. So let me describe this. So it turns out that if the time difference is less than pi, then there is actually unique light-like geodesic connecting these 2 points, and this geodesic unique. So there is a unique null geodesic potentially connecting these 2 points if you choose the angle properly, and those geodesic goes only around the boundary. Okay, so this light-like geodesic never leaves the boundary, and indeed it produces this singularity. But if you move this point more than pi, if you move the time difference more than pi, the new singularity appears. That is that there is actually light-like geodesic staying on the boundary going this shortcut, but there is actually a detour that you can, light-like geodesic can make, which goes inside of the bulk. So it makes a shortcut in the bulk, but in the other direction. So this gives rise to new kind of light-like geodesic that you had not expected. So after actually we worked through this, and then we found how this can be resolved. We found this paper that 15 years ago by Véronique Hubner, Honryu, and Mukunda Rangamani, where they actually noticed this singularity, and they called that as bulk-cone singularity, and they pointed out that this is some kind of new non-perturbative phenomenon, the new non-perturbative singularity that you would expect for final temperature CFD. But I would like to point out that these actually singularity are not there, that they are actually resolved. In fact, there are more. So for example, if the time difference becomes bigger and bigger, then you can have a situation where this light-like geodesic winds around black hole and then escape to the boundary. It never actually go inside of the photon sphere by the definition of photon sphere. So that means that eventually it stays near the photon sphere for a long time and then goes out to the boundary. So in that case, the singularity appears when phi is equal to v gamma times t, where v gamma is the speed of light for light going around near the photon sphere measured at infinity. So it's given by this formula. This is actually faster than the speed of light, but as we will see, it does not lead to causality violation. So anyway, so now you find that you have a new kind of singularity. So in addition to, so this is a phi t diagram. So in addition to this boundary null singularity, if the time difference is greater than pi, you have a new branch of singularity where phi, then this asymptote to phi equal v gamma times t. Okay. In fact, there are even more, because you can have a situation where null geodesic goes to the boundary, bounce off and go back to this point. So Daniel asked, why doesn't it picture violet causality? I'm going to explain soon. Okay. But before going to that, let me describe these pictures. Okay. So you have this, you can have bounce once, or you can have bounce multiple times. Or you can actually go have null geodesic winding around and bounce and winding around and bounce back. You can have such a situation. Due to conservation of energy and angular momentum, you find that number winding before bounce and after bounce has to be the same. So there are some kind of kinematical constraint. So by taking this into account, you find that you have all these new branches. So new branches appears every time t passes. T increases by pi. So between 0 and pi, there is only physical branch. But between pi and 2 pi, you have new branch. And for 2 pi and 3 pi, there are 2 unphysical branch and 1 physical branch. But note that this is actually mod 2 pi. So you have to fold this in order to actually have a singularity on the boundary. And if you do that, then you actually singularity is like that. And to answer Daniel's question, where everything inside of this light cones is okay. So that's sort of explanation. So even though this is faster than speed of light, but these are still inside of the light cone from the point of view of source from here. So it's okay. So these of course do not violate causality, but these are extra singularities that you should not expect from a CFT point of view. From CFT point of view, you can only expect these blue singularities. And in fact, these red singularities start accumulating for large time difference. And so it's kind of surprising that you have something like that. And in fact, if you calculate this kind of thermal two-point function in free CFT or rational CFT, you can find that these singularities are not there. So how can these singularities be resolved? So that's a kind of question. So let's look into, let's put this in the context of string theory and see how string theory helps us. And in order to do that, I need to tell you a little bit more about null geodesic in ADS-Schwarzschild geometry. So this is something you learn at the beginning of general relativity. You solve geodesic equation in geometry. So in this case, you have two conserved quantity, energy and angular momentum. So you solve that, and then then geodesic equation is just like this kind of Newtonian equation in the potential. So this is kind of effective potential. So it turns out that null geodesic is obtained in the limit when angular momentum and energy goes to infinity, whereas keeping ratio finite. And that's easy to see because this dot is actually a derivative with respect to proper time. And if you go to a null geodesic, proper time goes to 0. So that means that the energy and the angular momentum goes to infinity. You can see this more explicitly here. So suppose you have 2 points on the boundary connected by null geodesic. So let's call that time difference T naught and time difference, angular difference phi naught. So with this difference, these 2 points are connected by null geodesic. Suppose you have neighboring geodesic, which can be space-like. And so let's call the difference to T and phi. Then you can see that with this parameterization, they are related by this equation. So you see that null geodesic depends only on the ratio, but as E and L goes to infinity with ratio phi fixed, then T actually goes to T0 and phi goes to phi 0. So you can see that as L and E goes to infinity, the space-like geodesic go to null geodesic, for example. Okay. So I just transcribed this over here. And so, for example, in a situation where a geodesic winds around photon sphere many, many times, then the energy and the angular momentum goes like that. And indeed, as phi approaches to V gamma times T, where T, V gamma is the speed of light measured near the photon sphere measured at infinity, then L and E goes to infinity. I told you that we can expect from general discussion due to Adammer that Green's function would have singularities there, but you can actually easily check by yourself when in this kind of simple analysis. So when mass is large, the boundary conformal dimension is large, then a 2-point function would go like that. Okay, so e to the minus ml. So this is less than 1. So how can it be possible that it diverges when e to the minus ml, which is e to the minus ml, and both m and l are positive? The problem, it happens because you have to do ultraviolet cutoff and renormalization. So L is a geodesic distance from boundary point to boundary point, but you have to do UV cutoff because distance to the boundary is infinite. So you cut it off, and then you calculate this, but then you have to remove this one. But if you remove this one, then you multiply infinite factor over here. So that makes up for this. And in fact, you can see that if you calculate this for large L and M limit, it goes like this. So you have to remove this infinity coming from 2 times, actually not minus infinity in the exponent. So you have to multiply infinite factor to compensate for it. And then even though this was less than 1, but after this procedure, it becomes greater than 1. And in fact, diverges in the limit when the geodesic goes around photon sphere many, many times. So that's a kind of singularity. And I would like to explain how this is resolved. So it is resolved by the tidal force near the photon sphere. So there is actually a very nice formalism called tidal tensor formalism formulated by Mark that is sort of give you a covariant way to describe tidal force. So to do that, you choose a geodesic, and then you choose coordinate along the geodesic, which I call U. And then there are, so in 3 dimensions, for example, you have a triad, and then you Fourier transform them. Triad also normal to this geodesic. And then you contract this Riemann curvature by this triad, and it's called tidal tensor. The reason this is useful is that the metric near, for example, almost like geodesic can be described in this way. This is very much like Penrose limit, except that this formalism is more general and can be used not only for light-like geodesic, but for other geodesic too. And for ADS-Schwarzschild black hole, these tidal tensors are exact, where one direction is the radial direction. So you have this direction which goes around the photon sphere. And then there are radial directions, that's phi 1, 1. And then there are 2 angular directions. So you can see that if you put this on the string worldsheet, this is an unstable direction which try to stretch the string. And then there are 2 directions which try to squash string. This is what you expect from how the tidal force works. But notice that there is L square to it. So that means that as geodesic goes near the towards null, this tidal tensor grows. And so basically the effect that as you approach the right geodesic, then the tidal force grows and then starts stretching and contracting. And from the point of view of string worldsheet, that means that you have some kind of time-dependent perturbation to the string worldsheet dynamics. And that generates particle production on string worldsheet. But by particle production, I mean not creating more and more strings, but creating oscillation on the string worldsheet. So suppose you are calculating two-point function. So what you would do is that you specify from the beginning what kind of string state you want for this point and what kind of string state you want to capture on this point. So, okay, so you specify particular stringy state or point particle state on 2 points on the boundary. But so you send this particular particle to the bulk and goes around, but then string worldsheet starts generating particle production and creating oscillation on the string worldsheet. So by the time this string gets to the end point, you find somebody else. So I thought that I was sending Daniel near the photon sphere, and he goes around and around and creating other things like Monica or J1. And by the time I tried to detect Daniel, the particle became Monica. So I say that, well, this is the two-point function is suppressed because the probability of detecting Daniel decreased because some of the probability went to J1 or Monica or Liang. So that's what happens. And you can quantify this. So there we actually evaluated this in two different limits. One is the limit when the time difference is slightly bigger than pi. So in this case, actually, the geodesic are staying very far away from black hole. But even if a particle, the geodesic is far away from black hole, when you approach the light geodesic, then the tidal effect becomes large. So as far as you have finite amount of curvature, this enhancement happens. But anyway, so when in this case, actually, you can use sudden interaction approximation that you run in undergrad. And then you can calculate two-point function. So you start with Daniel and end with Daniel. But then because the particle goes to other oscillations, so in the end, the probability amplitude of detecting the same particle at the beginning and at the end gets suppressed as L goes to large, because as L goes to large, the tidal force becomes large. You can also have similar effect when the null geodesic wind around a photon sphere many times. So in this case, actually, what happens is that the particle stays most of the time near photon sphere. So actually the interactions are very, the time dependence is very weak because you stay in similar situation. So you can actually calculate this by using adiabatic approximation, the opposite of the other approximation. And then you can obtain this answer. And you get a different dependence on various things, but it's also still exponentially suppressed in L. So if you, by turning this into calculation of two-point Green's function, then you find that the singularity is resolved in string size. Namely, what happens is that if the two boundary point approaches to would-be singular point in the resolution of null singularity, in the resolution within the string scale, then you start seeing the resolution of the singularity. Where is the alpha in the formula? So I set alpha to be 1, excuse me, but you can easily recover that by dimensional analysis, I hope. So, so I think that alpha must be, in this case, a numerator, because this exponential suppression is suppressed when the alpha becomes small. You can also do similar calculation in asymptotic flat black hole. So in this case, actually, the calculation is slightly different, because the structure of the asymptotic infinity is different. So in particular, you don't have a situation where geodesic bounce the boundary and come back. And so you only have one branch. But except for that, the calculations essentially is the same. And But the difference is that you only have one branch and it's connected to the physical branch. So for small t, you have, so what happens is that therefore, for small t, you have a sharp singularity that you expect. But as t goes to large, the singularity becomes blur and blur by string scale. So this raises the question of whether you can detect something like that by event horizon telescope. And this is a long shot, but we took it seriously and we actually estimated this effect. And the reason for this is that this kind of image is actually due to the fact that you have light cone singularity, exactly the kind of light cone singularity we are talking about. So that means that if this singularity gets resolved, then this image may be modified, and then we want to estimate how much this singularity gets modified. Especially the geodesic winding around many times would have significant effect. The null singularity will be significantly resolved when you consider light-like geodesic going around the horizon many times. So when we calculated it, unfortunately, in order to detect it, as you might have expected, that you need a resolution of frequency in the frequency domain. You need a so you actually, in order to reconstruct this image, you work in the frequency domain. And in order to detect that, you need a resolution of the order of string scale. So therefore, you want to be able to see it. That's what you might have expected, but we estimated it anyway. So that's all I wanted to tell you. Thank you for your attention, and thank you again for the invitation. And I'd be happy to take any questions.
Thank you very much for a very exciting talk. So it's now time for questions.
Daniel is raising hand, and he is panelist, so he can speak up.
Yeah. Well, so I was just wondering, actually two things. One is, can you say a little bit more about why string theory is really important here? If say you just had particle interactions, those can also change one particle to another particle, but maybe they don't
by tidal effect. But tidal effect won't change particle species, no? Suppose
it would be a different interaction, right?
You send electron.
Yeah.
Well, so here I'm ignoring interactions. So I should say that, for example, suppose so there are other ways that singularity can be resolved. So for example, in this first example, there's a potential possibility also where you have black hole forms here. And the black hole decays, and then as you can consider high energy black hole scattering, and then that can resolve. In this case, actually, it turns out that is subleading, but if string were not there, that may save you, for example.
I see.
But here, we are considering just free particle approximation. So if you send the electron, even if you go around near a strong curvature regime, you end up getting electrons. No? So it seems like, at least in this case, you need a stringy, some extended object in order to feel what's important is the tidal effect changes the particle. If you have a string theory.
I see. Yeah, and the other question was, is there anything in the limitus? It goes around many times. The geodesic gets quite close to the black hole, and in particular, if it gets as close as the stretch horizon, I might guess that there's something interesting, or somehow the approximation.
Yeah, so that's a very interesting question. So that was actually my original motivation with Matthew, that we wanted to see whether we can probe what's happening near the horizon. But unfortunately, for Schwarzschild black hole, non-rotating black hole, you cannot go inside of photon sphere because it's a definition of photon sphere. The photon sphere is the same as the saying that where the speed of light is what you call the cosmic velocity or something that you go horizontal directions and you go outside of so you cannot go inside of a photon sphere. So photon sphere is like some fraction bigger than horizon. But one interesting possibility is that if you consider rotating black hole, then actually photon sphere becomes smaller and smaller. And in the limit of extreme curve, when the black hole rotates at the limiting velocity, then photon sphere coincide with the black hole horizon. So that's potentially interesting. And Matthew and I have been looking into that, but there is one thing discouraging, which is that even though in the standard coordinate, it looks like these are approaching to each other, but there are some finite geodesic distance between them in the limit. So even though you can go pretty close to the horizon, but in that case, but you still are not directly on the horizon. But it's a very interesting thing. I wanted to see whether there are other situations where this is possible. Okay, did I answer your question? Okay, he raised a hand. Okay, any other questions?
Monica raised her hand.
Yeah, she can unmute herself.
I believe I can speak.
Sure,
that was a beautiful talk. I was wondering if you can then detect these singularities in the perspective and the boundary, like in the CFT limit. If you can analyze something of a direct influences, or can you bootstrap it?
Yeah, so as I said, singularity is resolved, but it's still of the order of string size. So that means that in the regime, if you can do some analysis in strongly coupled CFD, then in addition to the strict singularity along the blue curves, where you would expect that there is a sharp singularity, but there are some bump with small string size support along each of these. And they tend to accumulate to a big time difference. So that may be something that you can still consider understanding from strongly coupled CFD at finite temperature. Well, I don't have a tool to do that. So I have not looked into that, but I think it's interesting. Thank you.
All right. So I think that time's up. So we should let's thank Hiroshi for giving such a nice talk. So and then let's move on to the next speaker. Next speaker is Leah McAllister. Can you share the screen?
Yes, here I go momentarily. Is that working all right? Do you see just the shared PowerPoint?
I see the PowerPoint. Can you start the slideshow? Great. Yeah, sorry for some possible background noise. There's some construction going right next to my office. Okay, so let's begin the next section. So next speaker is Leah McAllister from Cornell, and he's going to tell us about string vacua and axions.
Thanks a lot for giving me the opportunity to speak here. And I should say right at the start, just like Hiroshi said, please, if you have any questions and I'm not noticing them in the chat, I hope you'll call out and interrupt and let me know. I'm happy to take questions during the talk. So the line of work I'll be talking about today has the goal, the computation of the string landscape. And by that I mean we'd like to understand through enumeration what's possible in quantum gravity. This is, in a way, a bit of a counterpoint to the idea of trying to argue what's not possible. And what we'd like to do is construct ensembles of vacua whose phenomenology we can study. And to do that, we're going to need to develop some tools that simplify and automate the task of computing vacua. And with those tools in hand, we can explore and characterize some new classes of solutions. So the talk has two parts. The first and larger part is about the advances we've made recently in actually constructing vacua. What I'll describe is some software that we've produced for computing the data of certain classes of string compactifications, and I'll explain how we've used that software to find vacua in which the supersymmetry breaking by the flux superpotential is exponentially small. And then in the last portion of the talk, I'll give an example of how vacua of that sort can teach us something about axion physics, or at least we can think about axion phenomenology in that context. And the topic there will be superradiance in class of flux compactifications, superradiance around astrophysical Kerr black holes. So this work is based on collaborations with some excellent collaborators both here at Cornell and elsewhere. It's appeared in the last couple of years, and then we have a few more works coming out this summer. So let's start with the Sitter space. This is the simplest explanation for the observed universe. And so a very conservative approach to that fact is to try to construct de Sitter solutions of string theory. And pretty much everybody can agree that de Sitter solutions are not common. Faced with that, a search for them is not going to succeed immediately. Any possibly successful search is going to have to survey a large number of candidate geometries. But doing such a large search is not feasible with pen and paper. And even if we manage to partially computerize some of the tasks, the steps that still have to be carried out by humans are going to be rate limiting. So what we really would like to have is an efficient implementation of every step in the search for vacua, so we can do the whole thing rather automatically. Actually, each step is hard. The presently available tools in string theory are not very well adapted toward finding semi-realistic solutions. I would even say that exact non-supersymmetric solutions of superstring theories that actually have gravity in them seem out of reach, even in the present century. But that's exact solutions. We just need approximate solutions. And in most of physical physics, as opposed to mathematical physics, that's all we ever have is approximate solutions. And the issue here is not a cosmological one. It has nothing to do with de Sitter space specifically. Despite all the progress in understanding the standard model in string theory, we still don't have a derivation of the standard model plus Einstein gravity with no light moduli to the standard that I think all of us are demanding of de Sitter constructions. The problem is just supersymmetry breaking. But the fact that non-supersymmetric compactifications are hard to construct doesn't mean that they don't exist. It just means that we'll have to struggle a little bit in trying to find them. So what we need is some sort of systematic approximation scheme. And we know the fundamental expansions are in alpha prime and GS. So a natural approach, which is conceptually easy, but in fact is not the one that we will follow because it's hard to implement, would be the following. You first find some solution that preserves n equals 1 supersymmetry in 4 dimensions. So for example, a compactification of a type 2 string theory on an oriental fold of a Calabi-Yau threefold. And in that supersymmetric effective theory, you directly compute alpha prime and G string corrections to n to the k LO, so some number of orders beyond leading order. And then if you have that in hand, well, you can just look and see, are there, for example, de Sitter solutions in the EFT that only take account of corrections up to n to the k minus 1 LO? And then if you had such a thing, you could show that the last ones you were able to compute, the smallest ones you could compute, are in fact negligible. And that would be a well-controlled construction. Of course, it's unlikely, in general, following the Dine-Seiberg type reasoning, that such solutions will exist, but they might exist, and this is how you could try and find them. Now, more practically, we're going to have to apply some more approximations. The general strategy is typically to find parameter regimes where different sectors decouple into what you might think of as modules, different parts of the internal space, that interact weakly in a way that we understand. You can then analyze the modules in isolation and then weakly couple them. The trick if you do that, though, is you have to assemble all the pieces in the end, and that's going to be a key challenge that I'll discuss. So our aim in our line of work is to work under a particularly bright lamppost, Calabi-Yau compactifications. And we'd like to systematically compute the topological and some of the geometric data that enter the 4-dimensional effective field theory for a vast ensemble of Calabi-Yau threefolds. And in this vast ensemble, we'd like to automate the construction of vacua. In time, this may reveal controlled de Sitter vacua, or it may not. So on the left, I'm showing some of our recent works in this area, actually over the last 7 years or so, and then a very selected list of works by others along rather similar lines. So where are we going to find such a huge collection of lampposts to look under? We really need to try a lot of different candidate geometries, so where will we find them? Well, the largest known set of Calabi-Yau threefolds that one can play with now are those that arise as hypersurfaces in toric varieties. So a 4-complex dimensional toric variety is a complex manifold that can be obtained from a triangulation, a suitable triangulation of a suitable four-dimensional lattice polytope. So here are the two-dimensional lattice polytopes that obey the reflexivity condition. That's the suitability condition I was referring to. So there's just 16 of these. And here are some triangulations of them, right? So you see the square has two distinct triangulations, for example. Now, Kreutzer and Skarka famously classified and in fact listed all 473 million four-dimensional reflexive polytopes. And then we recently proved at Bound that the number of resulting triangulations is at most 10 to the 428. So that's definitely enough things to look at, but how can we actually go ahead and look at them? So the advantage we're living off of here is combinatorics. So in principle, you could try to find vacuum solutions of string theory, which after all are Ricci-flat compact manifolds, by solving PDEs. But nobody actually does that. One can live, as many have, off of proof of the Calabi conjecture and try and find topological conditions that guarantee the existence of a Ricci-flat metric. And that task is typically carried out in the framework of algebraic geometry, so instead of solving PDEs, you solve polynomial equations, which is obviously much better. But what's even better than that is when you can reduce the algebraic geometry operations to largely combinatorial ones and automate them. And then you can hand off the task to the computer. So if we're going to go about doing this, what should we really compute? So depending on what you're trying to build, what kind of, say, de Sitter construction or standard model construction or what have you, you might need different pieces of data. So we should try to get everything, by which I mean at least everything that follows directly from the topological data. So just as a laundry list of some of the technical objects we might want to compute, if you start with the four-dimensional polytope from the Kreutzer-Skarka list, you find a suitable triangulation that defines a toric variety. And then what can you do? You could try and compute the intersection numbers of the Calabi threefold hypersurface. I'll call it X in the toric variety. You could compute the Kähler cone of the toric variety, the Kähler cone of the Calabi threefold. You could compute Gopu-Kumar-Vafa invariance, counting curves in X, so telling you about instanton corrections to the prepotential. You could compute the cone of effective divisors. You could figure out what the orientifolds are, find F-theory uplifts of the orientifolds. You could try and find divisors that support Euclidean brane contributions to the superpotential. And maybe you could even try and compute a metric. Right, so where do we stand on these things, at least with regard to the capabilities in my own group? For this upper group that's marked in green, our computations are fast, they're automatic, and they're complete. We can get basically everything rapidly. For this next category, they're still fast and automatic, but not quite complete. There's some gaps here and there. We have developing capabilities in the stuff marked in yellow, and we have essentially no capabilities to compute perturbative corrections. And that'll govern our strategy. So let me tell you a little bit about how we've developed capabilities for this. My students Mehmet Demirtas and Andres Reyes-Tascon have written a software package called CY Tools. And what it does is analyze triangulations and the associated Calabi hypersurfaces, and can do this orders of magnitude faster than other publicly available codes like Sage, which are more general purpose, I should say, but for this task, CY Tools is far stronger. So as an example, what I'm showing here is a plot of the Hodge numbers, so H11 on the horizontal axis, H21 on the vertical axis, of Calabi hypersurfaces from the Kreutzer-Skarka list. And the complexity of finding a triangulation grows roughly exponentially with H11, because H11 turns out to tell you the number of points in the four-dimensional polytope. So triangulating a polytope with more points takes more time. There are more choices of triangulations. The complexity grows exponentially, but you can go all the way up to 491 in this list. And codes like Sage and other kinds of codes can typically explore this purple stripe all the way at the left edge. And the thing is, almost all of the candidate triangulations occur at the extreme right edge where the Hodge nut, where H11 is largest. So we're missing almost everything if we can only explore the left margin. So the progress we've made on this is as follows. When we got started, it took hours or in fact, was not possible to compute stuff outside of the region marked in purple. And now we can do most computations in milliseconds and then the hardest computations in at most seconds. So you can explore anywhere in here with relative ease. You can easily generate hundreds of thousands of examples or millions of examples overnight. What we expect in the next year or so is to be able to automatically construct classes of orientifolds and also to compute GV invariance. Not everywhere in the list, but over a large portion of it. So just as an example of the kind of stuff we can construct, I took the, in principle, hardest Calabi-Yau threefold in list. It comes from a polytope with associated H11 equals 491. I see there's a question in the chat. Why is there a lower bound on the Hodge numbers? Why is the bound so low, or why is there a lower bound? The reason there's a lower bound on Hodge number, I mean, they go down to just 1. So although H21 can secretly go down to 0 in more exotic cases, why is there such a low upper bound? I don't think anyone knows why it stops at 491 rather than some much larger number.
Actually, my question is that in the previous slide, it looks like there's a lower bound on the Hodge numbers. It's like strictly greater than I mean, some number. So is that the case or no?
Well, each individual one can go down to 1. So for example, you have the quintic 101 and the mirror quintic 101, 1. So 1 is possible. But if what you're observing is that, if you fix, say, H21 is, let's say, no more than 5, then you'll find that actually H11 cannot be any smaller than, it turns out, 70. So yeah, there are such bounds, and I don't know how to derive their origin. One can just observe that they are present. So yeah, in fact, there are whole papers devoted to trying to find Calabi-Yau threefolds, not necessarily from Kreuzer-Skarka, that have pairs H11, H21 that are both relatively small, and that's not so easy. Typically, once you make one small, the other one gets very big.
Thank you.
Yeah, thanks for asking. Okay, so what are we looking at here? This is the threefold with the largest, highest dimension Kähler moduli space. It has 491 Kähler moduli, and this is a two-dimensional cross-section of the Kähler cone. Each little polygon here is a distinct triangulation of the ambient toric variety. And there's quite a few of them to move through there, and for some kinds of problems, you want to actually explore that whole space. So clearly, you're not going to be able to work on this with pencil and paper. Okay, so now let me transition to describing what we can actually do, not just compute, but actually find. What kinds of vacua can we find? So the application of this will be to vacua with small superpotential. And I should stress, although everything up until now has been about let's do this computationally, what I'm going to tell you about now is analytic. It's fully specified by a small list of rational numbers. It's just that we had some computer assistance in finding it. But there's nothing either approximate or sort of brute force about what I'm about to describe. So if you're trying to find de Sitter, it's very helpful to have a sense of what you're looking for. So you might be able to find de Sitter in here. But if you have an artist's impression of what de Sitter looks like, then it's actually relatively easy to pick out where de Sitter is. And so the artist's impression of de Sitter that we'll be living off of is the KKLT scenario for de Sitter vacuum in type 2b string theory. So let's consider a compactification of type 2b string theory on an orientifold, call it X, of a Calabi-Yau threefold. And let's suppose that this geometry includes certain quantized three-form flux, an n equals 1 supersymmetric pure super Yang-Mills sector on a stack of D7 branes, and a warped deformed conifold region, i.e. a Klebanov-Strassler-Throat solution. Each of these things in isolation is well understood. And let's suppose that in this conifold region there are one or more anti-D3 branes. Then the claim of KKLT is that in a suitable parameter regime, these sources can yield a metastable four-dimensional de Sitter solution, and the corrections to all the approximations are small. So just a little more detail about the setup. The closed string moduli are the axiodilaton, H21 complex structure moduli, and H11 Kähler moduli. And for presentation purposes, I'll assume H11 is equal to 1, although in our detailed examples it won't be. So how do you go about finding such a configuration? Choose some quantized three-form fluxes. And then the four-dimensional n equals 1 supergravity theory is characterized by the flux superpotential due to Gukov, Vafa, and Witten. It's just the integral of the three-form flux wedged the holomorphic 3-0 form over the Calabi-Yau threefold. And that superpotential gives supersymmetric masses to the axiodilaton and the complex structure moduli. So for generic choices of F3 and H3, the quantized objects, the result is that one finds isolated supersymmetric solutions in the complex structure and axiodilaton sector. But the Kähler moduli are unfixed. And so below the scale of the complex structure moduli masses, one has an effective theory that just has the Kähler modulus, if I assume there's just one, and I can evaluate the flux superpotential on the vevs of the complex structure moduli, and let's just call that evaluated thing W naught. So just some complex number. If now we consider a stack of D7 branes that support pure glue, SU, and C super Yang Mills, the superpotential takes this form, so the sum of the flux part and the non-perturbative part. And this supergravity theory has a supersymmetric ADS4 minimum. And at that supersymmetric minimum, so you can just solve for the F flatness condition for T. I've drawn the potential there. And it's very easy to check that the minimum is at large volume, so the Kähler modulus is large in the minimum, only if W naught is exponentially small. Okay, so T at the minimum is like log of modulus of W naught. Now, there's a statistical argument that although W naught small compared to 1 is not generic, I should say W naught small compared to 1 in string units is what I mean. Although this isn't generic, it should occur for some of the exponentially many choices of flux, so maybe such solutions do exist. Okay, this was convincingly argued a long time ago, but you might want to ask more, like, can you really find these? So one thing you ought to ask is, do there really exist consistent global models that have quantized fluxes giving a small classical superpotential, and that have warp conifold regions, and that have suitable gaugino condensates, so that the whole scenario holds together? And the answer to the first two questions is yes, we've shown this recently. And for the third question, I won't say anything about it today. So today I'll just, I'll dodge the question, which is an important one, it's one that lies a little bit ahead of us, of exhibiting an explicit and fully controlled compactification that unites all the necessary components, including anti-D3 branes. That's for the future. For today, I'll just talk about items 1 and 2, small superpotential and a warped conifold region. And for those, I can give definite answers. So why do we need a small flux superpotential? As I said a moment ago, the smallness of the superpotential ensures the largeness of the Kähler modulus vev at the minimum. And so to control the alpha prime expansion, you need small W naught. And you might say, well, if small W naught can happen, why not just look for it with these fancy computational tools? The trouble is that it's exponentially rare, first of all, and it occurs preferentially in the high dimension moduli spaces. And so that's a frustrating computational task. It would really be better, rather than exploring these kinds of moduli spaces, rather than a brute force search, we should try something a little bit more clever. The previous record, by the way, is W naught about 10 to the minus 2. So it's better to invent and apply a mechanism, and we build off of mechanism from Gurevets et al. in 2003. Okay, and so here's an artist's impression of racetrack, which is the mechanism that we will be making use of. So what's a racetrack in a superpotential? So suppose you have some complex scalar field Z. We say that Z has a racetrack superpotential if W of Z, which is something generated by instantons, is a sum of, let's say, 2 terms. It could be more, but let's stick to 2. With positive, well, with negative exponents, so P1 and P2 are positive numbers, so these are 2 decaying exponentials. A1 and A2 are some prefactors. Let's assume they're constants for now. And as Z gets big, along the real line, this goes to 0. Okay, let's just think about real Z for now. So the idea is, let's try and figure out A1, A2, P1, P2, so these 4 numbers, such that the potential, the scalar potential, is minimized at some Z min that's large. If that's the case, then since this potential decays exponentially toward large Z, we'll find that W evaluated on the minimum is small. So this is a mechanism for small superpotentials. This is a very old idea. So you easily find, if you just try and solve for the minimum of the scalar potential for this superpotential, this is what Z min is. And if you just take that Z min and plug it back in and evaluate W instanton at that Z min, you get this formula. Okay, but the point of writing this formula is that W at the minimum will be small if the thing in the big round brackets is a small number and the exponent is a large number, right? Because then you have a small number raised to a large power. So if you can arrange that the exponents P1 and P2 occurring in the superpotential are close to each other but not exactly equal, and you can arrange a modest hierarchy in the prefactors A1 and A2, then you have a mechanism for generating a small superpotential in the vacuum. Now, this is an artist's impression, but you'd really like to see if this has some possible incarnation in string theory. And it would be reasonable to conjecture that since this accomplishes something quite nice for you, you might conjecture that it can never happen in a bona fide string theory compactification. Okay, and so to investigate that, one really ought to check whether these conditions can be met. So first of all, is it the case that the flux superpotential is the sum of two instanton terms like this in some cases, with exponents that are nearly equal but not exactly equal, and with hierarchical prefactors? If we can do that, we'll have succeeded, because then the Gukow-Fafowitten flux superpotential will be given by this formula on the right, which is a small number raised to a large power, and it's a small thing in string unit. So for the first thing, the instantons come from type 2a instantons wrapping curves of the mirror Calabi-Yau threefold, and we established a sufficient condition on the topological data for the superpotential to take the form required in item 1. For part 2, we just found explicit examples. So let me just show you an example. So let's call x tilde the Calabi-Yau threefold hypersurface in this weighted projective space, and x is its mirror. Its mirror has 272 Kähler moduli and 2 complex structure moduli. And so what we did is we just took that x, found an orientifold, and we found quantized fluxes, so that this particular direction in the moduli space is a flat direction. So the complex structure moduli space is 2 complex dimensional, and this is a particular direction in which the speeds along the 2 moduli are in the ratio 4/10 to 3/10. Okay, so this is some particular direction that's a flat direction, and along that flat direction, the superpotential evaluates to this object. So z is the coordinate along the flat direction. C is some overall number, written at the right. And you see that this does take a racetrack type form. The 2 exponents are 4/10 and 3/10, so they're close, but they're not exactly equal. And there is a hierarchy in the prefactors. One of the prefactors is 1, and the other is 5/288. And so as promised, this is all strictly specified by some rational data. And I'll show you in a minute that the omitted terms are small. So if you just take this superpotential and apply the racetrack idea, you find the moduli stabilized at weak coupling near large complex structure, and the superpotential is small, 10 to the minus 8. Schematically, you can understand that as being the hierarchy to the power of the ratio of the exponents, as shown there. Okay, so let's check that this is well controlled. First of all, what I've shown you is totally explicit. In the leading order data, there's no unknown factors. So there's nothing that we have to assume is order 1. It's just a finite set of computable rational numbers, and we went and found some cases where we could compute them and they turned out right. The higher order terms are strongly suppressed. So if we look at the prepotential, in blue are the ones that I used, and in red are the first ones that I neglected. They're a factor 10 to the 5 smaller. The next order is another factor 10 to the 5 smaller. So one remark, one of the complex structure moduli has a mass of order W0, which is small. It's not 0, but it's small, so one has to think a little bit about that, but I can comment on that if there are questions. Further comment is we very easily find many more examples of this type with, in fact, smaller values of W0. So what do you need? Well, you need to be able to compute the prepotential, including instanton terms. So you need to compute Gopu-Kumar-Vafa invariance. You need to find a suitable orientifold. And you need to be a little bit lucky with the numbers, the exponents P1, P2, and the prefactors, and the D3 brane charge tadpole. But you only need to be polynomially lucky to get a vacuum at small W0, at exponentially small W0. You don't need to be exponentially lucky anymore. And this is why this is not such a hard brute force search. We very often succeed. If you just start with a reflexive polytope and follow this whole chain, you often manage to find a vacuum of this type. So that's nice. Regarding conifolds, by analytically continuing our solution to near conifold loci, away from large complex structure and toward the conifold part of moduli space, one can find, we found, vacua that have not only a small W0, but also have a warped conifold region. So that means that, in principle, there's no problem in unifying this with the rest of the KKLT construction. A hard piece of work will be putting antibranes in such a conifold and exhibiting control. That's not something I'm claiming in any way here. We're just talking about supersymmetric vacua today. So the upshot is that small W0 is in the landscape. We've given examples, very well-controlled examples. But for KKLT, we certainly want more. We want to stabilize the Kähler moduli, and in the example I showed you, there's 272 of them. So you might wonder if there could ever be a rich enough structure of instanton contributions to stabilize such things. And we would like to understand supersymmetry breaking in the end. So in the last couple minutes, let me just briefly describe how black hole superradiance how black hole superradiance goes in the Kreutzer-Skarka axivers. So I'll explain in a minute what I mean by the Kreutzer-Skarka axivers. And this part of the talk is an example of what kind of phenomenology you can think about, or you can imagine studying, once you have in hand techniques for generating large ensembles of vacua of this type. And you can see a talk by Virav Mehta on Friday about this same work, where you'll get many more details. So axions are almost unavoidable in string theory, and sometimes they're pretty numerous. In the examples I was showing you, the number of axions could be several hundred. They result from integrating p-form potentials over p-cycles inside the compactification. And in the absence of some kinds of effects that create monodromy, there's a perturbative shift symmetry for the axions that's only broken by instanton effects. And the instantons, for example, the instanton action might take the form of the tension of a p+1 brane times the integral over the cycle of volume form plus p-form potential. I see there's a question. I think I'll address the question about FRW in the Q&A, if that's all right. If there's another question for during the session, please let me know. So in the absence of monodromy, there's a perturbative shift symmetry broken by instantons which have action of this kind of form. And in the regime where the alpha prime expansion is well controlled, meaning where the cycles are large in string units, well, this vol evaluates to something big, and so it's very easy to find many ultralight axions, because one is exponentiating the tension of a p+1 brane times the volume of a p cycle. So, and there's no naturalness issue in those fields being so light. They're not scalars, they're pseudo-scalars, they're protected by the symmetry, etc. So an axiverse is the term coined to describe a theory with many axions, and we might call then the theory that we're constructing, the class of theories we're constructing, the Kreutzer-Skarka axiverse. It's just the ensemble of axion theories resulting from type 2b compactifications on Calabi-Yau hypersurfaces. So we constructed 2 million geometries from the Kreutzer-Skarka list with up to 491 axions, and we examined about 100,000 of them in great detail. The general form of the potential is a constant matrix kinetic term, and then a sum of periodic contributions to the potential with some scales, lambda a, that are given by exponentials of volumes of cycles. The eigenvalues of the kinetic matrix are related to the axion decay constants, and the QAIs are the axion charges carried by instantons. So we just computed these data in terms of combinatorial inputs and moduli VEFs in a series of works. You can ask about a lot of different kinds of phenomenological outcomes in this setting. Inflation, quintessence, dark matter, birefringence, strong CP, etc. I'll just tell you very briefly about black hole superradiance. So the phenomenon of black hole superradiance is a long-studied one. A Kerr black hole can lose angular momentum to a cloud of axions and can then spin down. So if we see a spinning astrophysical black hole, you know it hasn't spun down too much, so you can bound what kinds of axions might be out there. The axions that tend to give rise to a superradiant loss of angular momentum are those whose Compton wavelength is comparable to the black hole Schwarzschild radius. So for stellar mass black holes, that's in the 10 to the minus 11 to 10 to the minus 14 electron volt range, and quite a lot lighter for supermassive black holes. There's another condition, which is the axion self-interactions shouldn't be so strong that they disrupt the condensate before it can suck angular momentum out of the black hole. That condition is just a lower bound on the axion decay constant. And so the measured spins of black holes end up constraining axion theories. The key point is that this is essentially independent of the cosmological model. We're not relying on axions being produced as relic particles or being part of the dark matter or anything else. They just have to be present in the Lagrangian, and they will cause spin down if they're in the right mass range. So all you need to do is compute the masses and decay constants, so we went and did that. We computed these in our ensemble. And the results are as follows. I'll just show you the mass, decay constant, and then we'll be able to get the constraints from that, and then I'll conclude. So the mass distribution is shown here. You can view this as like a histogram. It's a kernel density estimate. On the horizontal axis is the log base 10 of the mass of the axion in electron volts. Right-hand side is the Planck mass, left-hand side is the present-day Hubble scale. And the two pink bands are the superradiant bands for stellar mass black holes on the right and supermassive further to the left. The different colors of the lines correspond to different numbers of axions. point of this is that the axion mass distribution passes comfortably through those bands. And then secondly, the decay constant distribution. So here, the color coding tells you how many axions there are in the theory, from 1 up to 491. And here the horizontal axis is the log base 10 of the decay constant in GeV, so going from the Planck scale at the dotted line on the right. The point here is that these are in a range where they don't always disrupt superradiance. And so you can just take those data. It took us a while to get those data, but once you have them, it's pretty easy to put them together and understand which geometries are excluded by superradiance. And let me just call your eyes to the red curve in the middle first. Let's not look at the yellow and black yet. So what we're plotting is the fraction of geometries that are excluded versus Hodge number. So you see that for geometries with like 100 to 200 axions in them, a good portion of Calabi-Yau threefolds are excluded in our so-called default model. On the other hand, if you dilate the size of the whole space, everything gets so light that the axion mass distribution doesn't pass too far through the superradiant band, and there's not much of a constraint. That's the black line. Bottom line, it depends a lot on how you model where we are stabilized in the Kähler moduli space. But you can see that for some regions in the Kähler moduli space, you can exclude half the geometries right off the bat. And this doesn't rely on any dodgy assumptions other than this one thing that I'm describing, which is where one lands in the Kähler moduli space. Okay, so let me conclude. In most of the talk, I was explaining that the KKLT scenario requires special structures in flux compactification, an exponentially small flux superpotential, and a warped conifold region. And we presented a mechanism for constructing such solutions via a racetrack of worldsheet instantons in the mirror. We gave complete explicit examples, and so we've shown that small W naught is in the landscape. Our search is automated, it's possible to do large-scale studies, but the quantum side of KKLT and an uplift to de Sitter are very much works in progress, and I haven't made any claims about them yet today. But it's already possible, as I explained at the very end, to infer some kinds of constraints coming from axion physics, including from measurements of astrophysical black holes. Thanks very much for your attention. And I'm happy to take questions now.
Thank you very much for a very nice talk. So it's time for questions. Actually, there's one question in the chat by Owen Hogan. Maybe you can read.
Yeah, right. So the question from Owen Colgan is, as regards to motivation, LRW is coming under a bit of pressure. There's a cosmic dipole discrepancy. And the case outside of that realm, the case for de Sitter in the late universe would require revision. I would say, I would stand by the statement I made at the beginning that all things considered, it's still the simplest description. And from the more fundamental point of view of the utility of trying to construct de Sitter solutions, it's also the case that we rely on quasi-de Sitter solutions for by far our best explanation for the very early universe. So we don't just have to be motivated by the dark energy. I think we'd be faced with almost the same question, even if it turned out that we lived in, let's say, matter and radiation, matter-dominated FRW with no cosmological constant. We would still want to understand where the CMB came from. We would still want to understand inflation, which is essentially de Sitter, although quasi-de Sitter. And so then one would be faced with the same kinds of construction questions. So we basically need to resolve, I think, the question of de Sitter solutions in string theory one way or the other, and sub-realm by sub-realm within string theory, as a starting point for building cosmological models, but it would certainly be interesting to understand alternatives.
Hey, there's a question. So a question from Pablo Soler. Let me allow him to talk.
Hi, can you hear me?
I can, yes.
Hi, Liam. Very nice talk. I had two small questions, I think. One is when you try to get, when you're getting this small W naught, basically you're first setting a flat direction after including the Gukov buffer-Witten superpotential, right? And then
absolutely,
it's just worldsheet instantons. But I shouldn't think of W naught in this case as the Gukov buffer-Witten superpotential anymore.
It is the Gukov-Witten superpotential, but it's not the one that comes from the perturbative part of the prepotential. So it's literally integral G wedge omega, but in evaluating that, you need to specify what the prepotential is to get the superpotential. And if you were to take the prepotential to be given by the purely perturbative part, then you would get 0 along the flat direction. And all we did was take that 0 and add back to it the instant they were always there, but as an artifice you can imagine ignoring them. And we then consider the instantonic contributions to the prepotential. These are the type 2A worldsheet instantons. And those are present anyway, and it's a racetrack of those. So it's a little confusing because one would be tempted to say that, well, we sort of took a classical thing and added quantum corrections, but there are quantum corrections on the mirror. On the type 2B side, it's all classical. It's just that these are the classical ones that happen to be 2A instantons. Right. Does that address the first question?
Yeah. Perfect. Okay. Thank you. And the other question was just something that you mentioned that you haven't addressed, whether you have Young sectors which give gauge condensation, but do you expect any reason why the small w naught would conflict with
no.
that property, or is just that it has not been addressed?
No, the only thing you might worry about, and I'm not saying I'm particularly worried about this, is you might say, well, if small w naught, actually this is related to the remark that was raised when I was showing the Hodge numbers plot, what it's with these lower bounds. In the examples that we're looking at that have, because of our computational limitations, they have pretty small H21, they have pretty large H11, like so 272 in this example. And you might think, and I'm not encouraging you to think this way because I don't think this way, but one might say like, well, 272, that seems like a lot of instantons. I don't think it works that way. It's pretty clear that sometimes you have an awful lot of instantons. The trouble is, computationally, to demonstrate that all of them are good ones, it is a bit of work, right? You want to make sure that every one of them has like a Pfaffian that you can control, and that it's not like you have 272 good ones and one that's always problematic or something. And so that's really the only task. I don't see a reason for an obstruction, no.
Thank you. Thank you very much.
Okay, Sunju.
Hi. I find that I can turn on video.
Yeah.
So yeah, thank you for the very nice talk. So I actually also have a couple of questions. So the first question is about a technical side. So you say it's now feasible to work on large H11 cases, unlike in SAGE. And I'm wondering if you could elaborate a little bit on this, why it is feasible now. And
yes.
And the next question is about the racetrack part. You said it's you only need a polynomial lock, not exponential lock. And so I'm wondering whether you could also elaborate on this. And
sure, yeah. Sure, absolutely. So with regard to the first point, so SAGE is outstanding general purpose software for these kinds of computations, but it was never optimized specifically for these particular problems in the case that the number of points in the polytope is large. I mean, if you think about computer graphics, it's obvious that people can triangulate extremely complicated point sets. But what you have to do is find a fine star regular triangulation of a point set with this very modest seeming number, like 491. The problem is that the number of possible triangulations that could be Calabi-Yau threefolds is still super large here. It's 10, as I mentioned, if I can bring this up, which I can't, 10 to the 428. And so what did we do? Well, we basically identified that in the computation there were a sizable number of steps, each one of which we could make a few order of magnitudes of improvement on, and we just improved all of them. Sometimes there was an important idea, sometimes it was just that no one had thought to try to optimize away from H11 of order 2 to 5. So most works in the like 2010 to 2015 era, and certainly before, would study H11 up to maybe 4. You see a lot of systematic scans of Kreutzer-Skarka up to H11 of say 4 or 5. Because off-the-shelf software can just do those cases. And once you get bigger, well, each individual calculation that you want to stretch into that regime, you spend like a mini project making it work. But if you want to compute all this stuff, you need to make everything work. And so that was the labor that my students undertook and eventually succeeded at. With regard to the question of polynomial luck, that's just the simple fact that one is exponentiating a ratio here. So in this racetrack construction, one has the superpotential at the minimum is some ratio of some prefactors. So these are Pfaffian prefactors. In the case of two-way worldsheet instantons, they're just Gopakumar-Vafa invariants, so you can just directly compute these things. And these P1 and P2 are also exponents showing up in the instanton exponents. So these are all well-defined objects, and this calculation, the classic racetrack calculation of minimization, takes those numbers and maps them to a power, right, a ratio to some power. And you only have to be a little bit lucky in how these numbers land to find that you're distributed on a log scale, rather on an exponential scale in terms of W naught. So that's a fairly simple fact. The challenge was to be able to find cases where, in fact, you got just a little bit lucky. And to do that, we had to find cases where the GV invariants came in sizable ratios. You know, you want one GV invariant to be maybe 100 times larger than another one, or something like that. But such cases exist, and we found them.
Thank you.
Okay, probably the final question in the chat window by Songchan Park. So he asked, how robust is the exclusion bound on geometries? Any issue from stabilizing the geometry when, for example, SUSY is broken at a low energy?
Yeah, great. Okay. So regarding the robustness of the bound, it's from the image, it's hopefully clear that it's not the least bit robust against changing my assumptions about where in Kähler moduli space we're stabilized. And you might even say, if in the first part of the talk I was saying that Kähler moduli stabilization remains a challenge, how can I be talking about vacua here? Shouldn't I have stabilized them? What we've done is we've quoted exclusions. So if you pick a point in the space of the real part Kähler moduli, so the saxions, you pick a point inside the Kähler cone, that defines an effective theory. And you can imagine that the saxions are given large masses by, say, perturbative corrections of some sort. We haven't constructed those vacua. You can imagine that they exist. And if such a thing existed, it would be ruled out according to this. So I hope that's going in the direction of the question. I took the question to be, depending on what low energy dynamics is, could that shift some of the fields around? Certainly, but as long as the result is to stabilize the saxions at some point inside the Kähler cone, we can read off what the constraint is at that point inside the Kähler cone. And these different colors represent our attempt to sample different regions to see how the constraints differ. And you can see the constraints do depend on where you end up being stabilized. So a task for the future would be to understand where does one really get stabilized by well understood high scale dynamics. That's open, certainly.
All right, thank you very much, Liam, for a nice talk. So let's move on to the next speaker. All right, Daniel, can you share your screen?
I can as soon as you give me permission.
Oh, you're not given the permission?
No, it says, oh no, I think because Liam is sharing. If Liam stops, then I think.
Oh, sorry.
Oh, yeah.
Okay,
sorry.
Now it's gonna work. All right, how's that?
Yep, that works. Can you make it as a full screen?
I think it is already, isn't it?
Yes. Okay. All right. So our final speaker of the morning plenary session is by Daniel Harlow from MIT, and he's going to tell us about global symmetry and the black hole information problem.
Hi, everyone. Annyeonghaseyo. Thank you for the invitation. Today, I will talk about this idea of a connection between global symmetry and the black hole information problem. I wasn't totally sure about the audience. I guess I thought it would be broad with particle physicists and cosmologists and so on, but I see a bunch of experts in the audience, so I apologize if the level's a bit low for some of you, but hopefully it's also good for some of you. So there's this idea that in quantum gravity, there shouldn't be global symmetries. It goes back a long way, in fact, longer than these references. I think there are certainly, I've heard anecdotes of people like Sakharov saying this much earlier, or Zeldovich even than what I have here. The basic idea is that you can destroy global symmetry. If you have a global symmetry, then you can take something that's charged under it and throw it into a black hole. And then that destroys the symmetry charge. So that's the rough idea. To make it precise, however, and to really turn that into a contradiction, it's been necessary either to restrict to continuous symmetries, where there's an argument in this paper of Banks and Seiberg from 2010, or to restrict again to this very controlled context of ADS CFT, which is what Hiroshi and I did a couple of years ago. On the other hand, requiring that the cosmological constant is negative is clearly too restrictive, as the cosmology members in the audience presumably know. Well, hopefully everyone knows. In our universe, yeah, we may not be quite sure if it's de Sitter or something else, but I guess most of us are pretty sure that we don't have a negative cosmological constant. So we need some kind of weaker assumption than ADS-CFT. ADS-CFT is really too strong to use something that, in the end, we hope has phenomenological applications, at least in principle. On the other hand, I'll try to convince you today that some kind of assumption is necessary, that you can't just, if you're completely open-minded about what you call quantum gravity, then there are examples of quantum gravity theories that do have global symmetries. And so you need to introduce at least some kind of principles before you can try to establish this conjecture that there are no global symmetries. So the goal of this talk is to propose a natural and I'll say sufficient condition for excluding global symmetries in quantum gravity. And so this is based on a paper I wrote with Edgar Shigulian last fall. And so here's the proposal. It's that in any theory of quantum gravity, where black hole evaporation is a unitary process consistent with the Bekenstein-Hawking formula for the entropy, no global symmetries are possible. So this is really saying there's a direct connection between the black hole information problem and the absence of global symmetries. Now, I'm not going to be able to prove this. I mean, this is not the kind of thing that we could imagine proving, given our current understanding of quantum gravity. But I'll give you two kinds of evidence for this conjecture. So the first is I'll show that this assumption does not hold in the quantum gravity theories that have global symmetry that I'll discuss in a minute. Okay, so this is kind of some converse. And then I'll also show that my argument with Hirose and ADS-CFT can be upgraded to exclude global symmetries in any theory of quantum gravity where the recent calculations you may have heard of the page curve based on the quantum extremal surface formula are valid. So you can kind of, in the places in my argument with Hirose where we used ADS-CFT, you can instead just kind of port in this technology of the quantum extremal surface formula and islands, and you can get to the same conclusion, but now without having to assume that the cosmological constant is negative, which is good, I guess. So, so that, of course, these two things don't prove the conjecture, but if you like, they reduce it to an assumption that the only way for black hole evaporation to be unitary and compatible with the Bekenstein-Hawking formula is as happens in these calculations. Okay, so that may or may not be true. We don't really know. But if we assume that it's true, then what we showed is that this conjecture that no global symmetries follows from that. So let's start talking about these simple theories of quantum gravity that do have global symmetries. So they're all in low numbers of space-time dimension. I'll start with the very stupid one. So you can just take the world line of a relativistic particle in 0+1 dimensions. The target space can be any dimension, but the world line of the particle is 0+1 dimension. So that maybe doesn't look like a quantum gravity theory, right? I mean, we all know the solution, right? E squared equals p squared plus m squared. That's the solution of this theory. But you can write it in a way that looks like gravity by introducing a dynamical metric GTT on the world line, and then the embedding coordinates x mu of the location of the particle. And this starts looking like some diff invariant gravity action coupled to some matter fields with some cosmological constant in 0+1 dimension. So at least if you look at this, you might call it a theory of quantum gravity. A slightly more advanced version of this, which Hirose also used in his talk just now, is the string world sheet, where instead of embedding a world line, you embed a world sheet with a similar kind of action. Again, you have some, so now it's two-dimensional instead of one-dimensional. You have some dynamical world sheet metric G coupled to some matter fields X. And both of these theories have Poincare symmetry in the target space as a global symmetry when you view them as 0+1 or 1+1 dimensional theories. And they're just, I mean, the theories are completely solvable. You know, there's nothing you can hide behind, and they do have this global symmetry. Now, on the other hand, neither of these theories have black holes in any recognizable sense. And so this conjecture of Edgar and myself would allow these theories to have global symmetries. So the fact that they do doesn't contradict our conjecture. There's a more interesting family of examples where you take this Jakiv-Teitelbaum gravity, which everyone and their mother has been obsessed with for the last few years, where you have some two-dimensional metric G coupled to a scalar field, usually called the dilaton, which is this phi here. Phi naught is a constant. There's some boundary term you don't have to worry about, but this is a theory where if you vary this action with respect to phi, you get an equation R equals -2. So this is a theory whose solutions have constant negative curvature, and so they're ADS. And you can do the usual things we do in ADS CFT, and then you can couple it to some matter fields, which I haven't specified in detail what they are. You just take any, your favorite matter CFT, at least as long as it's non-chiral, and you can couple it to this Jakiv-Teitelbaum gravity. And then the key point is that this is a renormalizable theory of quantum gravity. Okay, so there's no issue in the UV. You can do canonical quantization and construct the quantum theory as in Dirac's textbook. And in fact, you can solve it by doing a Weyl transformation to flat space. Now, when I say solve it, I mean you can reduce all the correlators to the correlators of this matter CFT. If you pick a strongly coupled matter CFT, then you may not be able to evaluate those correlators. But you can solve all of the gravitational dynamics and just reduce everything to the matter CFT. So in particular, if this matter CFT has a global symmetry, at least a global symmetry that doesn't have a mixed anomaly with gravity. So for example, we could take this matter CFT to be n Dirac fermions, which has a UN flavor symmetry. Then this symmetry survives canonical quantization. It becomes exact global symmetry. So this is another example of a UV complete non-perturbative theory of quantum gravity that has a global symmetry. And unlike the previous two examples, so that the previous two examples were kind of silly, but this example is not silly. It does have solutions that look like black holes. So it might sound like our conjecture is going to run into trouble with this theory, but in fact, we'll see that this quantum theory that you obtain by doing the canonical quantization of this renormalizable theory leads to black holes whose entropy is actually infinite. And so like in the CJHS model, if you're old enough to remember that, the evaporation of these black holes leads to remnants and not to a unitary cloud, a pure state cloud of the radiation. And so again, this our conjecture does not apply to this theory, which is good because indeed it has global symmetries. So just to, because I don't want you to get the idea that this global symmetries in quantum gravity can only happen in 1+1 dimensions, I can at least give you a 2+1 dimensional example, which is the oriented version of pure Einstein gravity in 2+1 dimensions with a negative cosmological constant. So there are various attempts to try to quantize this theory in Euclidean signature, which have led to a lot of confusion in the literature. But you can certainly, I mean, it's renormalizable and you can certainly quantize it by doing canonical quantization. There's no issues with that. And so when people ask you, does pure 2+1 gravity exist? In the usual sense that Dirac would have recognized, the answer is yes, it exists. And this, in the oriented version of the theory, so I use the word oriented here, what I meant was including only oriented spatial topologies, because if you do that, then parity is a global symmetry. And so then that's our last example of a global symmetry in quantum gravity is parity in this theory, in this oriented theory of gravity in 2+1 dimensions. And so you can again say, okay, what about your conjecture? So this theory has a global symmetry. So, and we know it has black holes, right? It has the BTC black hole. But in fact, if you try to compute the entropies of those black holes, you again get infinity due to divergent amount of topological structure that you can put behind the horizon of the BTZ black hole. For example, you could just think about the number of handles, which could be as large as you want with a fixed boundary energy. And in fact, if you try to quantize the moduli space of the topology, then you get another divergence from that. So again, these the black holes in this theory of quantum gravity do not obey the Bekenstein-Hawking formula. And so our conjecture does not require that this theory doesn't have global symmetries. Okay. Now, the fact that, so, you know, I presented these theories, they're good to think about. You know, on the other hand, maybe some of you are uncomfortable with these theories. I mean, they're, you know, they're a bit weird, right? I mean, they seem to not have many of the hard and complicated features of quantum gravity that we usually expect quantum gravity to have. The reason why they're so simple is because they're normalizable, which is certainly not a property of Einstein gravity in 3+1 dimensions, right? So Einstein gravity demands a UV completion of some kind. We can't just kind of take it fully seriously by itself. Now, you could nonetheless hope that there's some kind of UV fixed point of Einstein gravity, which is what's called asymptotic safety. And my expectation is that if asymptotic safety makes sense, then it would allow global symmetries and probably also violate the Bekenstein-Hawking entropy formula. But so far, there's no, I would say, no evidence that asymptotic safety makes sense. So in fact, instead, all of the UV complete theories of quantum gravity in 3+1 dimensions or higher that we do have come from string theory. And those are all holographic, right? So the fundamental description of these theories somehow lives in a lower number of space-time dimensions at some asymptotic boundary. And in particular, definitely the fundamental description is not like, here's a path integral over metrics and we do the integral, right? I mean, that was in these low dimensional examples, that was the microscopic description. But that's not what we expect to happen in higher dimensions, at least unless we believe in asymptotic safety, which I don't, maybe some of you do. Now, the best understood example of holography, of course, is this ADS-CFT correspondence. So here's the basic idea in case there are people here who are not experts, right? So it says that quantum gravity in asymptotically ADS space, so which is like over here, this person is living in, so this is the picture for ADS3. Time goes up, there's a radial direction and an angular direction. So here's somebody floating around in the center of ADS. I guess Hirose was drawing pictures like this also. And so then the idea is that this gravity theory microscopically is really defined by some conformal field theory that's living at the boundary. And as you can see from the picture, the number of boundary dimensions is one less than what you had in the bulk, which is what you would expect from this holographic idea that I mentioned on the previous slide. Now, one of the most important features of the ADS-CFT correspondence is this quantum extremal surface formula, which gives a bulk formula for the von Neumann entropy of a boundary subregion. So, you know, I could give a whole talk about this formula. I just kind of sketched it here very quickly. So again, I'm here drawing ADS3-CFT2. So if you take a boundary, so a time slice of the boundary is like this circle here. This, the disk inside is a time slice of the bulk. So a boundary spatial subregion, for example, would be like this interval here that I called R. And so then there's a bulk rule for computing the von Neumann entropy of R, of the state of any CFT state rho, or at least any reasonably semi-classical state on this subregion looks like. So there's an A/4G, which is good because we're computing an entropy. But then you kind of scan over all the surfaces here, which, well, they're codimension 2 in general, but here they're just lines, which are attached to the endpoints of the interval. And also you demand that it's homologous to the interval. So then you have to extremize the area of this over 4G plus some higher order corrections, plus the entropy of the matter fields in between X, R, and R. So that's some functional of R, and then you extremize that over XR. And if there's more than one extremum, then you take the one which is smallest. So that's called the quantum extremal surface formula. It's kind of the modern version of what was before called the Rutakinagi formula. So it was developed in stages by these authors over about 10 years. But now this is the version that we think is probably the one that's going to last. So this, I just will tell you that this formula turns out to imply something called entanglement wedge reconstruction, which just says that if you have any bulk operator lying in between this XR and R, so in this wedge here, which is bounded by the green and the blue, technically this is the domain of dependence of the spatial surface between XR and R, if you know what a domain of dependence is. So it says any bulk operator in this wedge here can be represented in the dual CFD just using operators that are supported in R. So this was, when I was growing up, this was a conjecture, this entanglement wedge reconstruction. People would fight it at conferences. Now it's been understood that it's true, and it's just a consequence of this quantum extremal surface formula. Now, this quantum extremal surface formula has been understood from many points of view over the last 10 years. One way of thinking about it is that it's, you can think of it as a feature of tensor networks. That was kind of the first sort of hint that there was something interesting, something deep going on with this formula already back in the work of Swingle in 2009. It's also been shown that a version of this formula holds in any quantum error correcting code. So I had some proof of that in finite dimensions. Monica and Kolkmeyer had some proof in infinite dimensions, and also later Faulkner, and Hayden and Pennington extended to approximate codes. And then there's also a way of thinking about this where you use the Euclidean path integral, the replica method, and you can try to give a derivation of this QES formula for rather general gravitational systems, which doesn't necessarily rely on special features of ADS-CFD. And in fact, neither did these two things here. And so although this formula was first sort of discovered in ADS-CFT, it's kind of gradually been understood that it's really more general than just ADS-CFT. And in fact, inspired sort of by the generality of the formula, in 2019, these authors were sort of brave enough to try to use it to compute the page curve of an evaporating black hole. And in fact, they found that it worked. So let me just remind you briefly about that, right? So the main problem in the black hole information question is that Hawking's calculation of the rate of particle production tells us that the quantum states of the particles are basically mixed in a thermal state as they come out. So as time proceeds, more and more of these mixed state particles are coming out. So the von Neumann entropy of the radiation is growing with time. But eventually the radiation is all that's left. And so looks like a pure state evolves to a mixed state, which violates quantum mechanics. So Page taught us to quantify this using this Page curve. So we plot the von Neumann entropy of the radiation as a function of time for the evaporating black hole. So Hawking predicted that it just goes up, 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 and then it stops when the black hole evaporates. But Page pointed out that if the evaporation process is unitary, then the curve has to turn over at some point and go back down to 0. And so showing that this curve indeed turns over and goes down has been one of the key requirements for solving the information problem. I wouldn't say it's the only thing that you need to do, but at least it's one of the things that's on the checklist that you have to do to say that you solve the problem. And so seeing it coming out of this quantum extremal surface formula is major progress, and there's been a lot of excitement in the field over the last 2 years coming from these two papers. Now, before I get back to global symmetries, I just actually want to tell you a little bit more about this quantum extremal surface calculation of the Page curve in the context of this Jakiv-Teitelbaum gravity, because that's very helpful to illustrate the points that I'm trying to make in this talk. So here's what a black hole looks like in Jakiv-Teitelbaum gravity. So remember, there were two fields. There was this dilaton field phi, and there was the metric. So the metric has this Schwarzschild type form. It's just a dimensional reduction of BTZ. So if you're comfortable with BTZ, you should be comfortable with this. the dilaton is just linear, which is a good thing for a dilaton to be. And then if you look at Euclidean gravity, then it tells you that the entropy of this black hole is just the value of the dilaton at the horizon shifted by this phi naught term in the action, which was basically the coefficient of the Gauss, the coefficient of the Euler character in the action. And so the space-time looks like this. It's this shaded green region here. So it's kind of a piece of ADS2. So this whole thing here would be ADS2, but then there's the boundary conditions on the dilaton restrict the boundary to just these finite strips here. And so then there's a Cauchy horizon here, which you can't go beyond. And so then there's a black hole horizon here. You would expect probably in a theory with, in a theory with matter that these red dashed lines here would be singular, just as they would be for the inner horizon of a near extremal horizon or black hole, well, for actually any charged black hole. What these papers of last year realized is that in this very simple setting of Joukhiv-Teitelbaum gravity, where you can solve the gravity exactly, there's a version of the information problem, which you can realize even here. And so what you do is you take this Joukhiv-Teitelbaum black hole that has two exits. So there's some wormhole connecting two ADS2 regions. And then you just connect one of the ADS2 regions onto some non-gravitational reservoir that allows energy to leak out once you turn on the coupling between the two sides. And so as energy leaks into the reservoir to increase, right? So before the interaction is turned on, it's 0. I'm getting a warning about my internet connection. Maybe J1, is the connection okay for you? It's okay? All right, I'll just ignore. Okay. I'll just ignore Zoom complaining. And feel free to ask questions, by the way. I'm happy to stop if I know I'm saying a lot of stuff here. So if people want to type questions, I'm happy to address them. The entropy of the reservoir you can compute, right, in this theory where you just do canonical quantization of the matter fields coupled to gravity. And here's a formula that you get, using the fact that you can solve this theory. So indeed, if you look at this, this is kind of like Hawking's answer, right? The radiation, the entropy increases with time. This is the increasing function, and then eventually saturates at some finite value. But what was pointed out by these authors is that at least if this phi naught parameter is finite in the action, then for a large enough initial temperature for the black hole, this coarse grain, this entropy of the radiation that you compute by using canonical quantization actually exceeds the coarse grain entropy of the remaining black holes. So there are two remaining black holes because you started with a wormhole with two exits. And at least if you trust this Euclidean formula here for the entropy, then in this regime, this entropy over here is too big, and that's exactly Hawking's problem. It says that the radiation somehow becomes too entropic to be purified by the remaining black holes. In fact, if we're just studying this theory using canonical quantization, then the theory is exact. So we just say, okay, fine. Nonetheless, this is the right answer. And this Euclidean entropy formula here, which is the analog of Bekenstein-Hawking for this theory, is just wrong. The right answer for the entropy is infinity. It's not this finite formula that we have here. So that's fine. And that's why I said that just like in the CGHS model from 30 years ago now, this theory, if you just take it 100% linearly as a renormalizable bulk theory of quantum gravity, it has remnants, right? So basically that means that black holes have infinite entropy. And if black holes have infinite entropy, then there's no information problem. Okay. And in fact, therefore, global symmetries are allowed, which we already saw this theory can have global symmetries, right? But the key point, right? So I mean, the key point that made everyone excited is that although this theory is renormalizable, we could nonetheless choose to view it as a low energy effective field theory, which we think is a holographic description. And if we believe that, then we should be allowed to use the quantum extremal surface formula to compute the entropy, since that's a feature of holography. But then in fact, what was shown in this papers, which is still a bit surprising years later, is that if you use the quantum extremal surface formula, instead of just using the bulk description to compute the entropy of the radiation directly, then you get a more complicated formula. So you get a minimum where one of the terms is just the thing you computed before, But then there's this alternative term here, which comes from a quantum extremal surface that includes this so-called yellow island region here in the interior of the wormhole. So this, so in this picture here, what I'm showing in yellow is the entanglement wedge of the radiation system. And then, so its entropy is the entropy of the union of these two yellow diamonds together with the dilaton evaluated at the edges of this yellow island here. And so that gives this term, this expression here for the entropy. So this is the page curve computed from this model. In fact, they don't put this formula in the paper. I can't imagine why, since conceptually it's the main result. In fact, I think our paper is the only one that has this formula, but of course they had all the ideas. They just somehow forgot to write the answer in the paper. I guess when you do something for the first time, that can happen. Okay, so now I want to go back to no global symmetries. So let's briefly recall the argument that Hiroshi and I had against global symmetries. So we did two versions of the argument. I think we can just focus on the picture on the left. So this was an ADS CFD. So our paper was 175 pages, but here's the one-page version of the argument. You just take the dual CFD, you split it up into a bunch of regions. Then you say that there were a global symmetry in the bulk. If there were a global symmetry in the bulk, then there would be a global symmetry of the boundary. So there would be some unitary operator U of G that implements the symmetry. Now, by the locality of the boundary theory, basically Noether's theorem, you should be able to split U of G up into pieces that implement the symmetry on each of these regions separately. But then you have a contradiction because the operator in the center is supposed to be charged under the symmetry, so it has to not commute with the symmetry operator. But these pieces of the symmetry operator on these regions, well, the thing is you can make the regions pretty small so that this charged object in the center is not in the entanglement wedge of any one of these regions. But then that means that actually this operator has to commute with all of these pieces. But then if it commutes with all the pieces, then it commutes with the U of G also. And so then therefore there couldn't have been a global symmetry in the first place. So to extend this beyond ADS CFT, we need a few assumptions. So like we can let S be a quantum gravity system. So this will be a little bit formal. So we just say we have some quantum gravity system that has black holes whose semi-classical description lives in D dimensions. And we let R be a reservoir system, which is weakly interacting quantum fields on RD, possibly including linearized gravitons. So then we just have to make a few quick assumptions. So we assume that we can couple them together such that the black holes in S evolve into R. We assume that we can use the quantum extremal surface formula. So that's where we're really using the power of holography, and moreover that we can apply it to the reservoir system as happened in this Jakiv-Teitelbaum example. And then we assume that we can couple them in any way that preserves the global symmetry. So roughly speaking, S is a black hole and R is its Hawking radiation. If you just want to think about it like that, that's fine. Okay, we have the black hole, it's coupled to the radiation via the usual Hawking process. And so then we just have the same contradiction that we had before. So here's the picture. So we just, so now here's our evaporating black hole. We take the Hawking radiation and we split it up into a bunch of pieces. Then we have the black hole system sitting here. And then we say we take so say we had a global symmetry. So then the idea is that there's this island region over here, which enters into the entanglement wedge of the radiation when the black hole is old. And so we just take the charged operator and we put it into that island. And then, so by entanglement wedge reconstruction, this charged operator, I should be able to represent it as an operator that has support only in the radiation. But on the other hand, this operator is not in the entanglement wedge of any piece of the radiation. And it's also not in the entanglement wedge of the remaining black hole system because it's in the entanglement wedge of the radiation. But so then this operator has to commute with each of the pieces of the symmetry operator, but then that just means it has to commute with the symmetry operator, period. And so then that's a contradiction and the operator can't be charged.
So here, are you assuming that entanglement wedge reconstruction beyond the ADS?
Yeah. But as I mentioned, that's a consequence of the quantum extremal surface formula. So I'm really just assuming the quantum extremal surface formula beyond ADS, that's right. With the excuse that, as I mentioned, things like the quantum extremal surface formula show up in all these situations that have nothing to do a priori with ADS, like tensor networks or error correcting codes or Euclidean gravity. Yeah. Yeah, right. But that's really the key ingredient here. I mean, that's the non-trivial input, is I'm allowing myself to use the quantum extremal surface formula. So you can try to quantify this a bit by looking at relative entropies. There's a nice paper by Henry Lin and Yiming Chen, and then there was also a related paper out of some West Coast couple postdocs around the same time. So that's basically it. There was a puzzling aspect of this, which I could say more about, but I think I won't, since according to Angie, I'm running out of time. Maybe if someone asks me. So I'll just say what the puzzle is and what our conjectured resolution is, but I'll omit the argument for it. So the question is, why does the quantum extremal surface formula give the wrong answer for the entropy of the radiation if you just take the theory that you get by doing canonical quantization of JT coupled to matter? But it gives the right answer in an effective theory, which is the low energy limit of holography. Okay. And so our conjecture is that the resolution of this is that you're really only allowed to use Euclidean gravity in holographic theories. The Euclidean path integral is when you in a gravity effective field theory with the UV completion, it only correctly computes the entropies if the UV completion is holographic. If it's just asymptotic safety or loop quantum gravity or some renormalizable theory in low dimensions, then you shouldn't be using Euclidean gravity. So in some sense, Euclidean gravity and holography are equivalent. Okay. And so I had a couple slides explaining why that's true, but I think I'll skip over it since we're running out of time. So I'll just say that, so maybe I'll just say the last thing here. So the idea is that we can think of the Euclidean gravity path integral somehow as restoring the minimal amount of UV information beyond what you would have gotten just from low energy effective field theory, which is necessary to restore high temperature, low temperature duality in the boundary description. At least in ADS CFT, that seems to be the justification for why the Euclidean gravity path integral is correct. Maybe I'll show this one picture here. Basically, the issue is that in the Euclidean gravity path integral, to get anything interesting, you have to allow the thermal circle to contract in the bulk. And if you're doing canonical quantization, that's not allowed, right? If you do quantum field theory, the thermal circle is not allowed to contract. So if you try to canonically quantize geometry, you won't get contributions to the partition function where the circle contracts. But if you're doing holography, then the real thermal circle is living at the boundary. And so then maybe it's okay for it to contract in the center. So that's kind of the core of the argument. We made it a little more mathematical than that. So apparently this sort of minimal amount of UV information about quantum gravity, which you get from the Euclidean path integral, is enough to determine the page curve and also to forbid the possibility of global symmetries. Okay, so I think I'll stop there. Thank you for listening. I'm sorry for going a little bit over.
All right. Thank you, Daniel, for very interesting talk. So it's time for questions. There's already one in the Q&A window.
Yeah. So they were asking. It was asking about when you say the second term. Unfortunately this format doesn't allow us to have back and forth. So I don't know whether you mean the second term the second term in the first option of the minimum, or the second term. I'll assume you mean the second term in the minimum. So that comes because when you use the quantum extremal surface formula, there was this global minimization that you do. So let me go. Yeah, here is the quantum extremal surface formula. There's this minimum. So you look for any surface that extremizes this combination of things, and if there's more than one, you take the minimal one. So what happens in this Jakiv-Teitelbaum story is that so you try to look for the quantum extremal surface for computing the entropy of the reservoir system, because the page curve is about the entropy of the reservoir system. And the options are that you just assume the quantum extremal surface is the empty set, and so you just do the bulk computation of the entropy here, and that gives you this first term. Or you do the bulk computation, but you include this island over here, where you say the entanglement wedge of the reservoir also has a piece that lives in the bulk, which is this island. And then if you include that, then you get a different formula for the entropy, which is this. And then you take whichever is smaller, because that's what the quantum extremal surface formula tells you to do. So, okay, I hope that answers the question. You can type a follow-up if it doesn't.
All right, there seems to be another question.
Yeah.
Okay.
Oh, okay, yeah. So there was a question about, right. So yeah, so in Lorentzian signature, so okay, so good. So this question of minimal surfaces is something that mathematicians have thought about a lot over the years. This is kind of a Lorentzian version of that. So minimal surfaces don't really make sense in Lorentzian signature because you can always get a surface whose area is very small by just making it be close to null. And so it'll be some weird jagged surface. It won't be something that has a vanishing extrinsic curvature, which is the thing that you might want. So in order to get something that makes sense in Lorentzian signature, you extremize instead of minimize. But then you somehow, if you have more than one, then there's still this other minimization step that you do. And so from a mathematical point of view, it actually looks a bit weird. And there's actually something that is actually more natural from a mathematical point of view, which is called the maximin prescription, where the idea is that you fix, so you first fix a Cauchy surface, then you look for the minimal surface within that Cauchy surface, and then you maximize that over all possible Cauchy surfaces. And so then there, I would say heuristic proofs, I would say they're not rigorous, that show that that's equivalent to this formula that I wrote down.
Okay, there's a question by Monica. So Monica raised her hand.
Okay, so maybe Monica first, and then I'll do Terada-san.
So Monica, you're allowed to speak.
Hi, I don't know what happened, but
I hear you now.
We thought I did unmute it. That was a really nice talk. Actually, you somewhat answered half the way that what I was going to ask, because I was going to ask, what do you feel about the Lorentzian signature and how much of the argument can process through, and perhaps certain parts might not really work.
Well, yeah, I mean, so this picture that I drew, like this one, is this Lorentzian picture, right? Like here's null infinity over here. So
I was wondering, in the gravitational path integral perspective, how much of this can actually work.
Oh, you mean just because you don't believe in Lorentzian path integrals in general?
You can say that somewhat.
Is that the flavor of the question? Yeah. Yeah. Okay. So I want to make a distinction here between gravity and quantum field theory. So in quantum field theory, the Euclidean path integral, there's nothing shady about the Euclidean path integral in quantum field theory. I had some comments about it here, right? I mean, you want to compute trace of E to the minus beta h, and you do the Euclidean path integral. That's it in quantum field theory, right? And it's actually in some sense better posed than the Lorentzian one, because the Lorentzian one needs some I epsilons floating around, and it's hard to prove that it really makes sense. But the thing is this, you know, the thing that's real in quantum mechanics, I maintain, although not everyone will agree with me, is the canonical formalism, right? The thing that's real that, you know, really tells you the physics is the Hilbert space and the operators. And so I believe in path integrals only to the extent that they can be derived from a canonical, you know, from a Hilbert space formulation of the theory. And so in quantum field theory, both the Euclidean and the Lorentzian path integrals can be derived from an operator point of view. The Lorentzian derivation has more phases and it's hard to be rigorous about it, but morally they can both be derived with sort of equal validity. But the Euclidean gravity path integral is in a different camp because this one can't be derived because it requires you to include, well, at least in the usual rules of Euclidean gravity, you have to include configurations where the thermal circle contracts. But as soon as that circle contracts, then you can't interpret this as a trace in the canonical Hilbert space, right? And so then you're computing a partition function that, unlike the quantum field theory partition function here, is not a trace in a Hilbert space that you know. And so, which is both the strength and the weakness of Euclidean quantum gravity, right? It's the weakness is that we don't know what we're doing, right? We just have this weird set of rules that we don't understand and we follow them. But then the result is it knows things that it doesn't have a right to know. Right, like it knows that S equals A over 4G without counting the microstates, right? Whereas if this were actually equal to the trace of something, right, then that trace would be over microstates, and you'd have to know what they were to compute it, right? But somehow Euclidean gravity computes it without knowing the microstates. So it's this kind of miraculous thing, and I mean that's something I've been saying, you know, for the last couple of years. Is I think many people do not appreciate how crazy Euclidean gravity is. You know, it's an oracle that knows answers, but they're not derived, and you have to, and in fact, you can get into trouble if you're not careful because you don't know what what the real principles are. I don't know if that helps, Monica.
Well, I guess.
All right.
I don't really know much about Lorentzian gravity.
Okay, shall we move?
Lorentzian gravity is where we live, Monica.
I know.
I guess should I answer Takahiro and then?
Yeah, let's first answer Takahiro Terada's question.
Yeah, so can you explain a little bit more about what is the identity? Well, sorry. So to be very clear, Takahiro, in the situation where there's a remnant, it's not string theory, okay? This is literally just like doing quantum gravity in the stupidest possible sense, right? You just take this Jakiv-Teitelbaum action that I wrote here, and you just do the path integral, the Lorentzian path integral, or you just do canonical quantization. And so that theory has remnants because since there's no UV, so there's basically because there's a horizon, but there's no UV cutoff. And so if you have a horizon without any UV cutoff, you can just pile up as many modes near the horizon as you want without a limit, right? And so the number of microstates of the theory that are compatible with a fixed energy is infinite. And so that's the mechanism. And so I called a remnant because, it's an object. So you can just put, you can put a cutoff at, 3 times the Schwarzschild radius or something. You can fit an arbitrary number of modes inside. And so an object with a finite energy, but an infinite entropy is the definition of a remnant as far as I'm concerned. And this remnant is exactly a remnant in the sense that people think about in the information problem, but it's not string theory. It's just doing, the path integral with an integral over a metric and matter fields.
All right, so time's up. So let's there is a 30 minutes break in before the next parallel session. So let's clap our hands for our great plenary speakers. Thank you. Thank you, Hiroshi, Liam, and Daniel for giving such a wonderful talk. All right, so people who wish to stay for a little longer, then I think we can stay a little bit for a chat. And yes, and for rest of the people, we'll resume from 10:50. Thank you very much all for coming in this early morning, especially.
Thank you.
Thank you, Hiroshi, for such a nice talk.
Yeah.
Can maybe before, are you busy or maybe can you spare?
I'm happy to chat
I
a
can
bit.
stay on. It's about the dinner time, but I can stay a couple more minutes.
Oh,
my son is in bed, so I have nothing else to do. I can hang out as long as you like.
That's